Hello again. So let's pick up where we left off here. So hopefully did those others, right? Hopefully they check out pretty well for you. Okay, so we're going to try some inverses with graphs. Now, these are not given to you on the graph yet. We have to make it. So when in doubt, you can always make yourself an XY or an X and F of X little input-output chart, table of values to make sure you got it. We know that if we plug in 0, we're going to get 0 into this function, so let's start with that. Plugging in 1, well, we get 1 cubed, and then we take a half of that, we get 1/2 out. Plugging in 2, we get 2 cubed is 8, half of that is 4. After that, it kind of goes off the graph, so we're really going to have to just plug in these values, right? We got 1 comma 1/2, 2 comma 4, right? 3 cubed is 27, a half of that is 13.5. It's going to go off the graph, right? Now the other side, right, what we're going to see is -1. That's going to give us -1/2, right? -2 cubed is -8. Take half of that, you get -4. Okay? So now I've got the basic shape of a cubic function, right? And I'm going to do the inverse by just going backwards. So the point, right? Now, I am putting this as, just so we kind of see where it's coming from and we don't assume that this is a function, right? Let's just take each one of these points and make them backwards, right? And we'll start with f of x and call that the input. But hopefully we do realize these are just switching, right? So now I can just plot these points, right? 4, 2, 1/2 comma 1. 0, 0 stays where it is. -1/2, -1. And -4, -2. Okay, so I get something that looks like... Oops, make that a little bit better. Looks like that. Should be nice and smooth, right? And I look at this and I'm like, wait a second. This definitely is a function, right? Both of these are functions. Here's f of x and here is f inverse of x. Now that I know it's a function, I can use that f inverse notation to say it. If it wasn't a function, it wouldn't make sense to apply an inverse to it, right? Okay, let's try this one now. X squared over 4, right? So I know this should be some sort of quadratic, right? It should be facing up. The over 4 part might make it a little bit trickier to graph, but hopefully not too bad. Okay, if I take my x and f of x, I'm going to start with 0, 0 again. Plug in 0, I know I get 0. If I plug in 1 this time, I get 1/4, right? 1 squared is 1, 1/4. Plug in 2, I get, well, 2 squared is 4 over 1, so 2, 1. The point 3, not the best point, right? But 9 over 4, 2.25, 9/4. Gonna do a little estimating there, right? 4 squared is 16 over 4, I get 4, so I have a nice 4 point. And then 5 is really the last one I can fit on this graph. So 25 over 4 is 6.25. Right? And those are just going to be estimations. 1, 2, 3, 4, 5, 6. They're going to be at my best estimations for those points. Okay? Now, the other part about this is I know it's symmetrical, right? I know it's symmetrical, so I can use the fact that -1 is also going to be 1/4, -2 is also going to be 1, all the way up to get these points on the other side as well. All right? And hopefully we see that this is just a quadratic or a parabola that is a little bit wider than the standard x squared. Okay? Now, I try to do the inverse here, right? I do f inverse, oops, I'm not going to use that notation yet. I'm just going to flip f of x and x, right? I always want to call it f inverse, but we got to be careful, right? 0, 0 stays the same, right? 1/4, comma 1, 1, 2, right? 2.25, comma 3, 4, 4 stays the same. Hopefully we realize, right, that if we're thinking symmetrically over this diagonal, right, this is where that symmetry can help us sort of imagine this shape going, you know, sort of nicely symmetrically. However, like we looked at last time, right, because of this symmetry going on, we also have this side. Oops. And most certainly, right, this is definitely not a function. Now, how could we restrict this so that we can see what the inverse, how can we restrict this function so that the inverse will be a function? Well, as we talked about last time, right, if we took just the section where x is greater than or equal to 0, right, then we don't run into that problem. In other words, it will correspond to this section of the blue graph. Similarly, you could have taken all the values where x is less than or equal to 0, would have corresponded to this part, okay? So, in order for these type of functions, right, to have an inverse, right, we need to do some sort of domain restriction. We talked about the horizontal line test last part, but today we're going to talk about, you know, what is a function called when it does pass the horizontal line test. So we call this function a one-to-one function, okay? And it's a function where each output, right, which really is like element of the range, y value, right? These are the common ways we talk about output. Has a unique or only one input. And this is an element of the domain or X, right? Okay. Now graphically, a function is one-to-one if it passes the horizontal line test, right? And here's a great example because we can see the original function did not pass the horizontal line test, right? You had the point 4, 4 went to negative 4, 4, right? We know that negative 4, 4, right? An output of 4 had two different inputs, right? That was no good. That turned out to be a big problem when we switched the x and the y to graph this, because now one input has two different outputs, right? So a one-to-one function will have an inverse that is also a function, okay? Now, we've done some horizontal line tests, but we're going to push it a little bit further and look at a couple ones over here. We have to make sense. Are these going to be one-to-one functions? So I want you to try the graphs out. Hopefully those are not too bad. And then I'll go over numbers 3 and 4 with you. Okay. Hopefully those were not too bad. 1, definitely not one-to-one. 2 is, right? It passes the horizontal line test. 4 does not. It fails it right here. And 5, it is. Now there is an asymptote here, right? There actually is no point on this graph that will have this asymptote. We'll look at these rational functions in more detail later in this course. And I want to talk about 3 and 6 really quick, right? For 3, if this is the function f of x, this is certainly a function, right? However, an output of b has 2 inputs. 1 and 2. It is not one-to-one, right? That is not a one-to-one function. You can also think about if you took the inverse would not be a function because b would be going to 2 different things, 1 and 2 for the inverse. So definitely not one-to-one. X to the 4th is an interesting example, and I give you a hint. Can different outputs give you the same input? Well, hopefully we can think about this as like, all right, if I try 2, what's f of 2? 2 times 2 times 2 times 2 is 16. 2 to the 4th, 16. Is there another value that could give me that same output? Oh, yes, there is. A negative, right? When you take something to an even power, it's going to be positive, right? When you take a real number to an even power, also 16. This is definitely not one-to-one. 2 inputs, x equals 2 and x equals negative 2, gave the same output. Okay. So hopefully that's okay. We'll start off another video with methods for finding inverse equations.